Well, so based on the basic theory that we worked out in the previous class, in this lecture, we will cover balancing of rotors, the practical things. The last class, we closed with the question of how to know the unbalanced masses or the information about the unbalancing so that we can do the limit. So this time in this lecture we will study the practical techniques to do the balancing. Basically, we will put balancing masses in such a manner that the thing gets balanced. And after that, what was the unbalance? In principle, we can determine it equivalent unbalance, but its purpose is already served. So there are two ways of doing the task. One is by using balancing machines. So in balancing machines, you have the framework with shaft and measurement devices, etc., etc., on which you can mount a carriage with the rotor, and then you can work out the balancing masses, which will balance the. So you mount the rotor on the balancing machine, and then you conduct trial and error experiments by balancing masses and their locations through measurement of amplitudes and amplitudes of magnitude. So, in one kind of balancing machines or pivoted carriage balancing machine, the entire unbalance is assumed to be in two chosen planes. Now, this is a standard thing in all the rotor balancing that we are going to handle, because with balancing masses only in two planes, we can balance anything. So that's what we do. Now, the carriage with the rotor is mounted with pivots at one of those chosen planes, call it plane 1, and supported by spring at plane 2. Then what happens is that since at plane 2, since it is supported by springs, so because of the unbalance, there will be vibration, and the oscillations, the vibrations at that plane can be monitored. Okay? So as you rotate at some respectable angular velocity so that measurements are sensible, the unbalance in plane 2 shows up as the vibrations, and the amplitude of that is measured. Now, this is first trial. Now, in the first trial, if you find that the amplitude is so small that it's already balanced, and then you are finished. But that is not typically what happens. So then you register some amplitude of vibration. Then you take a trial mass, put at some location on the road, and repeat it. Now, whatever amplitude of vibration takes place, measuring that is the more important. So, you along a circular say track, you put the same balancing mass at several places. 0 degree, 5 degree, 10 degree, 12 degree, 15 degree, 20 degree, and then adjustment a little bit here and there. And you try to get the amplitude minimum by adjusting the angular position of the balancing mass. Once you have found the angular position, putting the balancing mass at fixed position, you get the minimum amplitude. Then you want to further reduce the amplitude of vibration. So this is a number of experiments you keep on doing. It's trial and error. Then once you have found the angular position where you need to put the balancing mass, you say either you change the mass, or rather easier is to change the radial location, that is distance from the axis. So you adjust that a little bit so as to reduce the amplitude to almost 0. So once you have done that, then whatever is the original unbalance in plane 1 and plane 2, out of that the unbalance in the plane 2 will be highlighted. Now open it and interchange the 2 planes. Now pivot it at plane 2 and support the location of the plane 1 where you earlier pivoted by spring, and then repeat the experiment. Now in this round you will be correcting the unbalance in plane 1, and that's it. Now you can take the rotor, balance the rotor, and use it. So this is by using balancing machine. Now the rotor may be so big that you can't do that. For example, it's a huge hydroelectric turbine somewhere on the hill of Uttarakhand. Okay. So dismantling it from there, putting it in your workshop where the balancing machine is there, and having such a huge balancing machine which you can mount it, all that you are not doing. You let the turbine be where it is, and you go there and balance it. Okay. That is, for large rotors, the trials need to be conducted in the operating conditions or field conditions. That's why it's for field trials. Dismantling and mounting of balancing machines is ruled. So, field balancing, if most of the inertia is located within a narrow axial distance, say it's a thin disk, then it is basically internal balancing that you will need to do. On the other hand, if the rotor is something big, then you have to do two-plane balancing, right? So first consider the case of thin disks. Now there are two ways of doing it: either by measurement of amplitude and phase, in which case you will need two sets of measurements. The other possibility is measurement of amplitude if you do not have the phase measurement. In that case, you have to make more measurements. So this is actually very straightforward. So first we consider amplitude and phase. So what you do first, you now how do you measure phase? So at in one transverse direction, you measure the amplitude, and at the same time, the way the displacement varies, okay, that gives you a sinusoidal wave, and for measuring the phase, you need some reference. So the from the axis of rotation, you connect a sine wave generator, which you use as reference, and from that reference, you measure all the phases. Okay. So one round with the rotor only, you measure the amplitude and phase, and then the rotor and plate trials sum up and call that A2. The first one is A1, the second one is A2. Based on that, you can work out what should be the balancing mass and in which angular position it should be placed. So since you have measured amplitude and phase, so this A1 is a vector. You can take it as a complex number to be vector, okay, or phasor as theoretical numbers column. Okay. So, and then plot this much magnitude at phase theta. And then the A2 with the rotor and a trial mass, say empty, that you put as another vector at angle theta, whatever. And then by joining the the two tips of the two arrowheads, you get the effect of the trial mass only. That is A from A to B. Now, what would be nice? What would be the best? In which case you can take the trial mass right at that location where you have tried as a balancing mass. If AB turns out to be AO, that is, if coincidentally it happens that in the second measurement, see in the second measurement, if A2 is 0, then you would be here, and in that case, this AB would be AO, and that is what you want. Okay. So currently it is not so. So what you can do is that, see, this is the magnitude of the unbalancing effect of the balancing. You wanted it to be equal to 4, and you wanted it to be in the direction from A to O and not from A to B. So for that, what you do is that you multiply the current trial mass you take and multiply that with OA by AB. Then it gets scalar. 20-gram balancing mass, when you multiply it with this length by this length, then it becomes something like 28 grams. And then through this phi angle, if you turn in the axial position, then you get to the correct position where the effect would be, the effect of the trial mass would be this. So that is what we need to find out, and that's it. So A1 is OA, A2 is OB, A2 minus A1 is AB. And our problem gets solved if B coincides with O. So the balancing mass will be empty, the trial mass into this OA divided by A, which is this. And it should be located at an angular position of 5 counterclockwise. 5 angle counterclockwise. By calculation only you can do it by considering everything as complex numbers, and the complex number delta with which you need to multiply MT to get this complex number, balancing mass as well as at the angular position, and from that you just get delta, which would be this complex number divided by the negative of this complex number. So that way this and this will be equal and opposite and balanced. So this is how you do it if you have the facility to measure amplitude and phase. If you have the facility to measure only amplitude, then you say, okay, so I have to conduct 4 experiments. So measurement of amplitude. You conduct 4 experiments. First, in the condition of only the take the amplitude as 2. Second, you put a trial mass MT at this point, I mean some point, and call it 5 to 3. And whatever amplitude you measure, call it 8. Then you put the MT trial mass exactly at the opposite direction. The same mass exactly at the opposite direction. Q. 5 is 5. Then you get the amplitude, note it as 8. And then in between the two angular position at R, that is 5 into 5 by 2, you take the fourth reading, that is 8. Now start the construction. I mean, I have told here the construction as a graphical, but you can do the whole thing by calculation. Basically, what you need to do is that you need to construct a triangle with one side AB of length 2A1, another side AC with the length A2, and a third CB with the length A2. With 3 lengths, 2A1, A2, A3, you can construct a triangle. So that triangle you have to construct. So in a different way, the same thing has been mentioned here. Let us go through. You draw OB, which is A1, rotor, and then extend it backward up to A, so that AO and OB are equal. O becomes a midpoint. So AB turns out to be twice A1. Right? Now complete the triangle with AC as A2 and CD as A3. You see, we don't know the phases, so we don't know the direction. But since to complete the triangle, we now have two sides. I mean, one side we already have, the other two sides also we have. So from SSS, we can construct the triangle. Okay. After doing that, you say you after drawing the triangle. So the triangle ACB you have got. Now you try to work out the magnitude of the effect of the trial mass energy. And you see that will be OC. Why it will be OC? Because A2, which is AC, is AO plus OC. And AO is A1. So AO is A1. A1 plus OC. A1 was the unbalance of the A1 was the manifestation of the unbalance of the rotor only. Then OC must be the manifestation of the unbalance due to the trial mass at P. So together they should give you a vector difference or vector addition, whichever way you look at it. So A2 is AC, which is AO plus OC, that is A1 plus OC. So OC is the effect of the trial. And check it from the other side also. A3 is CB. A3 is CB. What is CB? CB is CO plus OB. OB is the same A1. This should be bar. OB bar. So OB is the same A1 on this side, and CO is minus OC. Minus OC. So this is the effect. Minus OC is the effect of minus OC is basically C. That is the effect of the trial mass at Q. It should be negative of what was its effect at P. So these two you have, and therefore you have verified that yes, indeed OC, the midpoint to the third vertex, that is the effect of the trial. Now, what you need to do? You have to multiply this trial mass with length OA divided by length OC, and then you have to turn it by angle phi. Right? So you have got it, but there is an ambiguity because the way we made the triangle, we could have made reflection here, C down here, B here. It would be same. In that case, it would be minus phi, right? So magnitude is found correctly. Okay. Magnitude of the effect of trial mass will be OC, which you can find out easily. Okay. Either from the construction or from the calculation, and that will be just that. So MT times OA by OC, you have got the balancing mass here. The direction by which you have to turn phi can be the other minus. So which one you don't. So in order to resolve that, the fourth reading and draw a semicircle with OC as radius and the semicircle extending 90 degrees on this side and 90 degrees on that side. So basically, perpendicular to OC, you draw a line, and with radius OC, you cut that line on both sides, call it P, call it F. Now, if OC is correct, then you see phi is this way as we have drawn and not its reflection. Then, by going from P to R by 90 degrees counterclockwise, this effect of the trial mass would turn from C to E. It would be O. Okay? And then the resulting A4 would be AO plus OE. The way this was AO plus OC for P, like that, now it will be AO plus OE, that is AE. So if phi is correct, then A4 should be AO plus OE, that is AE. Check this one too. Otherwise, if minus phi is correct, then A4 should be something else, right? And in that case, what would happen? It would be basically if minus phi is correct, then this entire thing, entire figure would be mirror image of this against this mirror AB. Then this F would be down like this, and AF would come like this. And in that case, this OC, which is here by right angle, would go to that AF prime. Okay, so OF prime. So it's mirror image. But magnitude would be the same because reflection does not change any magnitude. So in that case, the magnitude of A4, which we are measuring really, we are measuring only magnitude, that is amplitude, it would be equal to whatever we have got from AF. So if minus phi is correct, then A4 should be the reflection of A, and from the magnitude of A4 which we have measured, we can check which is correct. And then accordingly apply the balancing mass, which you work out like this. And at phi or minus phi, run it counterclockwise or clockwise by that much angle accordingly. So this is the field balancing of a field resistor. Now come to the big one, okay, in which we will consider all unbalance to be concentrated in two places, because we can always work out an equivalent distribution. So we treat the unbalance as concentrated in the two balancing places, call them the near end and the far end, N and F. Now we have to conduct three experiments or trials and measure amplitude and phase of the oscillation as you rotate. Now the three experiments are these. One is rotor only, and whatever is the complex number giving the amplitude and phase of oscillations at the near end, call it N1, and at the far end, call it F. So in the first experiment, you can get these two complex numbers as the F. In the second round, you put a balancing trial mass MTN at the near end, at the far end put that. And then again rotate at the same angular velocity and get the corresponding near end oscillations, amplitude and phase, far. Similarly, now remove this near end mass, trial mass, put another trial mass, MTF. These two need not be same. MTF at the far end. And then again measure the two complex numbers, means measure the amplitude and phase, MT and F. Now you can work out what is the effect of the near end balancing mass and far end balancing mass. Now the near end balancing mass has effect on both of them. Something here. So when you put the near end, this trial mass at the near end at the active location which you have marked for reference. Then you had the complex number showing the disturbance as N2. Without that, with the rotor only you had N1. The trial mass effect would be N2 minus N1. Similarly, at the far end, its effect would be F2 minus F1. In the same manner, the effect of MPF at the far end would be M3 minus N1 and F2 minus F1. Now, whatever are the effects of these two trial masses individually by superposition, you say that I would like to multiply this with a complex number and this with a complex number and put both of those trial masses together so as to balance completely N1 and N2. That is, so that effect of alpha times this and beta times this together should be minus N1 and minus N2. So MTN you multiply with the complex number alpha, MTF you multiply with another complex number beta, and then demand that alpha times this effect plus beta times this effect is minus N, and similarly alpha times this because it is here. Okay. Alpha times this plus beta times this it should be minus N1, and similarly alpha times this plus beta times this should be minus. Impose this. These are two complex equations in two complex numbers, alpha and beta, and you can solve them. I mean, if you are using complex arithmetic in your program, or if you have direct straightforward calculation of complex numbers, whatever kind of calculation facility you are using, then you can actually solve them as two equations, or you can always resolve into real and imaginary parts and get four equations and four numbers and solve whichever way. So you solve alpha beta from the knowledge of these six complex number arithmetic works. Whether you use that complex number arithmetic and take it down to four ordinary equations, real equations, or you use complex arithmetic in your program, it's up to you. So magnitudes of these two multipliers, alpha and beta, give you the scales by which you have to multiply the corresponding trial masses and their phases, their uh, arguments will give you the angular shift for placing the balancing that you have determined by scaling with the magnitude. And that's so this is how we balance rotors, and rotors are thus ICs which can be completely balanced. This is an important message because next we will take up balancing of IC engines which typically cannot be completely balanced. So in the next class, we will go to balancing of IC engines and explore how much of that can be balanced and how and what tricks and techniques can be employed to have the unbalanced. So these things we will study in next 2 lectures.